Hello there, this is lesson number 4. And it concerns beta decay and this is a new particle that you're being introduced to, beta decay and the neutrino. So here's your title. Just to recap about alpha, beta and gamma, we know that alpha is 2 protons and 2 neutrons. That's 4 particles altogether. It's quite large, it's quite heavy. We've covered this before, a couple of protons, a couple of neutrons. It's quite a large particle, doesn't go very far. 8,000 times more massive than our beta particle, which is just a negative electron. And lastly, gamma, which isn't a particle at all, it's a photon. Now, the important thing about all of these types of decay, whether it's alpha, beta, or gamma, is that all of these particles, or both of these particles, plus the photon of energy, are all produced from the nucleus of an atom. Don't get fooled into thinking that beta decay or beta radiation is because an electron that's orbiting a nucleus, say this is a helium nucleus, it's got 2 protons, say the helium atom had a couple of electrons in orbit. Don't get confused or led astray by thinking that a beta particle, which is an electron, is actually an orbiting electron. It's not. It's an electron that's emitted from the nucleus of a much larger unstable atom. So I'll write that down once I get rid of that bit. You need to make some notes, of course, on this. You'll be seeing a pattern. You'll need to make some notes. I'll give you some supplementary sources of information, which I'll put up as video links. But you need to make some notes, and obviously your assignment is going to be that you're going to submit a picture of these notes or some of these notes so I can see what you're up to. So that was just a recap, really. You should know that already. So we're now going to look at beta decay, which is an electron that's emitted from a nucleus. So here's a note about that. A neutron in the nucleus. So obviously it must be in the nucleus because they're nowhere else. A neutron in the nucleus decays into a proton. Now the proton stays in the nucleus. And if I'm going too fast for you, you can pause the video at any time. It remains in the nucleus, plus an electron, and that is the beta particle. That is ejected or emitted. So a picture of that might look like this. We've got a massive nucleus, and it needs to be massive because massive nuclei are quite unstable. They've got too many particles or too much energy, and a way of making themselves more stable is to get rid of particles. So a big nucleus like that of uranium, for instance, that's got hundreds of particles, will get rid of some of the particles. Now that could be 4 particles, could be 2 protons and 2 neutrons, which makes an alpha. So it's then become more stable by making itself smaller. Excuse me. It could be a beta particle because then the beta particle, the electron, is emitted and the nucleus has become smaller. Another way of making itself more stable is to emit a gamma ray photon, which is a burst of energy. So removing energy from a nucleus makes it more stable. So alpha and beta are particles that leave, making the nucleus more stable. And gamma ray emission is taking energy away from the nucleus, which makes it more stable. So you've seen some of this at National 5. So what happens is physicists have a way of looking at individual particles and setting up detectors so they can see what's going on, and they can determine that when the beta particle is emitted, the nucleus, the large nucleus, recoils, and that means the nucleus just shifts a little bit to the right. It's a bit like firing a gun. The bullet goes off in one direction and the gun recoils in another direction. So, and the beta particle comes out down here. Okay, but you'll notice this is not in line with the recoil. The recoil goes off that way. I'm just drawing this so it goes off horizontally. The beta particle comes out in the opposite direction, but not directly in line with the recoil. So what we want to look at now is two things. One of the things we want to look at is something called conservation of charge. And the other one is conservation of momentum. And we'll look at conservation of charge first. Now that basically means, look, we start off with a neutron which has got no charge, and we are left with a negative beta particle which comes out, but a positive proton remains in the nucleus. So let's look at this conservation of charge first. Okay, conservation of charge goes something like this. Charge is conserved. That means that all the charge beforehand must be equal to all the charge afterwards. So charge is conserved. Total charge at the start, before the beta particle came out. Total charge before is equal to total charge after. Now we haven't done conservation of charge before, but you can see it looks a little bit like momentum, that the total momentum before a collision or before an explosion is equal to the total momentum afterwards, and it's the same thing. So we've got a neutron, which is obviously neutral. So if we have the charge before is neutral, we must have the total charge afterwards is also neutral. Well, how does that work? Well, we have a positive proton and a negative electron. Can't write E minus inside a tiny dot, but its charge is negative. Now the charge on the proton we know is plus 1.6 times 10 to the negative 19 coulombs, and the charge on an electron is negative 1.6 times 10, there's a point in there, negative 1.6 times 10 to the negative 19 coulombs. And if you add these two charges up, you end up with nothing, which takes us back to this neutral or zero, no charge, zero charge here before. So we've got something called charge conservation in beta decay. So the charges before are equal to the total charges afterwards, and you can see that there. Okay, now I want to move on to not charge conservation, but I want to move on to conservation of momentum. And this might give you a bit of a clue here that this doesn't seem to balance out, that the recoil goes off here and the beta particle comes out here. And this led physicists to believe that there must be some other particle which was ejected or emitted at the same time, which came out in this direction. And then these two directions come together to give an overall effect, which is directly in line with the recoil. So that's like a sort of resultant, if you like, coming out that way when you take the beta particle that comes out there plus a new particle. So physicists then had to find out what was this new particle. So if you just look at the recoil and the beta particle, you'd say that momentum is not conserved because the directions are not cancelling each other out. So what we have to do is we have to make up another particle that comes out here, and we have to balance the masses. We have to look at the tiny recoil in terms of speed and mass. So we're going to look at the momentum of the mass of the nucleus here and the velocity of the nucleus as it recoils, and then we're going to try and balance that up with the mass and velocity of the beta particle at some sort of angle downwards, and the mass of the velocity of some new particle that we're going to discover here. And this new particle is called the neutrino. It's a very small particle and it has no charge. Now in Italian, the word, any word with ino means it's quite small. So a small child in Italian is called a bambino, which just means, means a small child. So neutrino comes from Italian, and the neutral bit, the neutron bit is there and the ino bit is there. So it's as if this new particle here has no charge and is very small, and it's got a very small mass. Well, in fact, it may have zero mass, and this is another thing that is quite modern with physics. We're not sure as physicists whether this neutrino that comes out has any mass at all, or whether it's just very, very small. And that's a bit of research which has been going on for some years now, is to try and detect neutrinos and capture them and measure them and try and see what their mass is. And we already know that their charge is nothing, but we're not sure of their mass. Okay, so the neutrino has a symbol, just like electrons have a symbol E, and protons have a symbol P, and neutrons have a symbol N. A neutrino has a symbol which looks a bit like a V with a little bit of a squiggle on it, and that is the Greek letter. It's like our letter N, but it's the Greek letter is pronounced nu, and you can see why they picked this Greek letter nu, because it fits in with neutrino. And it's also got a little E here, which actually tells you it's something called an electron neutrino, because it's a neutrino that is produced at the same time as this beta particle. Remember, beta particle is an electron, so it's something called an electron neutrino. So beta emission was discovered in the early 1900s. Neutrinos were discovered later, but then it actually took some more work to find out that this neutrino that was emitted here actually isn't a matter neutrino. It's in fact an antimatter neutrino. So I ought to put anti-neutrino here and put a bar across the top there. So what we've got here now is we can make up a sort of formula, if you like. We've got the neutron in the nucleus decays into a proton, which stays in the nucleus, with an electron that's emitted and an electron neutrino, or an anti-electron neutrino So there you go. There's a sort of formula for what's going on. So this is sort of natural evidence that antimatter exists, and it's also evidence for a brand new particle that had not been discovered before called the neutrino. So we're starting to build up our evidence for not just things like protons, neutrons, electrons, but we're now starting to think about positrons, which is an anti-electron, and anti-electron neutrinos, which are emitted, and that's antimatter, and a new particle, which is called the neutrino. Okay, so we've got that. Now, that there is a sort of SQA bit of knowledge that you need. Later on, we actually found some, not we, I've got nothing to do with this, physicists discovered that you can also get positron emission. So you start off with a neutron in the nucleus, you're left with a proton in the nucleus, and we're going to kick out a positron, a positive electron, and later discovered, lo and behold, a matter particle called a neutrino. So this one's actually an anti-neutrino, whereas this one, that's because it's antimatter, and this neutrino is a matter particle. So the SQA would like you to know that one, but don't really need you to know that one. But I just thought I'd throw that in because it involves some nice symmetry. Okay, so that just about wraps that up, and that's this lesson on beta decay and the neutrino.